In the next subsection, I'll show you a classic data structure that achieves exactly what we were wishing for in the case of a stack: have an array, but be able to change its size. Sounds contradictory, but we can work our way around this contradiction. I thought it's useful to say, to have on the slide at one point what an array is. So I tried to formulate the operations of an array here. Don't think of arrays as an abstract data type. Really, an array is a concrete data structure. Okay, I just used the language of an abstract data type here because it's convenient to say what an array is in case you wouldn't know. I mean, it has these three over. You can create an array of a fixed size, and you can do this in Python like this, even though there's no real arrays. It's just the closest approximation. You can do it in Java like this, and other languages look similar. You can get the position, the element at a position using square brackets, and you can write to that position in the same syntax in a way. You probably have seen this, so I don't want to spend much more time on this. The thing is, arrays are really part of the operating system of the programming language, so you don't have to create those yourself normally. So how can we get an array that changes size? Well, we cannot, but we can get a new array. So whenever we need more space, we just make a bigger array and use that instead. That's the whole magic behind this resizable arrays. So I formulated it here again as an implementation for stacks. The idea is essentially more flexible, but we'll come to that at the end. We had these two invariants from the array-based stack. We maintained an array S. Remember, I drew this so that it resembles this stack of books. And the trouble was it has fixed capacity C, so it has a height C. And we kept the pointer top pointing to whatever is the current topmost element that is in use. Now we want, I just postulated like that for now. We want that this capacity C is bounded in terms of n, or more conveniently expressed the other way around, the number of elements n. So n is the number of elements on the stack. Is that not somewhere on the slide? It better had be. Well, now it is. So the number of elements on the stack should be at most C. Well, we can't store more, but also not fewer than a quarter times C. If we can maintain this invariant magically somehow, we will always have space for more elements because the capacity magically matches up. But of course, we'll have to make that happen ourselves. And how do we do that? How do we get to the point that this is always true? By two little changes. Whenever we do a push, we first check if the array is completely full. If so, we double the size of the array. And what that means is we have to allocate a new array of double the size and copy all elements over. That sounds costly, and it is. Similarly, if we pop, and that was the last element that brought us below this lower bound, if the new size of the array is less than a quarter of the capacity, then we shrink the array. So it looks like this is the same, but remember that here n is really small. So again, we allocate an array that's twice as big as we currently need it. And we again have to copy the elements over. That's always the costly step we need. These two things together are usually known as resizable arrays. It's a bit of a misnomer because this is just what it looks like from the outside. Maybe the constants, these factors here are not always 2, but that's the basic trick, that that's used everywhere. And that's how Python lists are implemented, at least in C Python in the reference implementation. They use something like this doubling trick. Okay, let's have a look at, well, you know this stuff already. Okay, it's reloading. Maybe I can do it here. Should we go to 50? No, 60 again, right? 60 was it? Oh, no, Google makes me solve captchas. I'd love to be able to show there's, I can do it here. All right. I mean, try to resist the urge to change your answer. This is a fairly tricky question. I probably meant to not show you the result yet. Yeah. You'll figure out why the answer I already revealed is correct after the fact. So the bit we haven't touched on yet is what does this do to the cost of our operations? And the problem here is because this copying, I mean, creating a new array may or may not be costly. That's a bit of a question of what the memory management system does exactly, if it has to fill the array with initial values or not, for example. But definitely copying the elements on the stack to the new array is costly. So occasionally these push and pop operations can be really expensive. However, we would hope that this doesn't happen all the time, right? Because if you keep pushing, we made the array much bigger, so every costly operation must be followed by many cheap ones. And so the idea of amortized analysis is to try to offset these two things. Yes, some operations can be expensive, but you usually don't just use a single operation of a data structure in isolation. You use many operations, and then maybe it's helpful to spend more effort now and profit from it later. So in this concrete case, there's, again, this is a topic many of you will have seen in some undergrad class. There's different ways to sell the same idea. What I will show you here is kind of a bank account accounting metaphor, if you want. Whenever we do something that's expensive now but helpful in the future, we get credits, and we can spend credits in the future to amortize the cost. Yeah. Pardon? Not sure where you are on the slide. Oh, phi is just the name. I mean, it's a Greek letter. Yeah, it's I don't know how this came about. I guess it's not even the Greek P, so it's not like potential. I don't know where this comes from. I think it's from physics tradition that potentials are named phi. Don't ask me. It's a convention. It's just a name, right? It's just a name. So the idea is we define a quantity that we can offset real costs against. If we pay a lot now, we want the potential to cover that for us. And if we pay a little now, we want to build up potential. There's two ways to look at it. One is the credits world. That's borrowing, right? It's the North American world. You don't save up until you can afford the car. You go and buy it and buy it on credit and then pay it back. I don't know, the diligent German way is you first build up the savings and then you go and buy the car. For data structures, the two are not so different because you don't know what comes first, which operation comes first. This is under the control of the outside program. Let's try to walk through this. Maybe the example makes this clearer than my fuzzy explanation. We define this quantity phi, a mysterious thing. It's defined as the minimum of these two things, which if you think about it, let me draw a picture here. That's our current array, which has length c. So c is the size of this. I don't know, I probably need the space. That's c. And we have a current number of elements in this array. Say up to here, this is filled. And to the right is empty. Now, what this potential looks at is this distance, right? C minus n is how much free space do I have? And the other one is n minus a quarter of c. So you take the quarter point, that's this one, and you take this difference. Maybe colors, right? So that's the blue part. That didn't quite work. Blue? No? That's the blue bit. And say this is the red bit. That's this distance. So the intuition behind the potential is how close am I from the danger region? Well, how far am I from the danger region? And take the smaller. So take the one where I'm closer to another costly thing. And in this case, red looks a little smaller, so it's more likely that I have to pay to make the array bigger than make it smaller. So the potential measures this safety buffer, the size of the safety buffer. If you use our invariant, I formulated this in terms of n as a bound of c, but we can flip it around. If you rearrange this, then you get a bound for c, which is more convenient for this. And so if you insert what you know for c, you find out that this potential is always between 0 and 0.6 times n. That's just doing the calculation. Now, what we'll do is for each operation, we'll look at what is the amortized cost. That's the real cost, what I have to pay to do the operation, plus the change in potential. And to be precise, I multiply the change in potential by 4, just because that works out to be the right constant. There's no magic explanation. You try a constant until it works. So we define the amortized cost of an operation like this. And then we just go through the operations. So for push and pop, we have two different cases. If they're cheap, then the actual cost is one array access. So that's what I said here. Let's count the number of accesses to the array. That counts both reading, writing, and copying. So we kind of lump that together. The actual cost is one access. and we increase the potential, we lose at most 1 credit. It's minus the change in potential. Why did I do it like this? So it's natural to think in credits here. If we look at the negative potential, then it's credits that we build up. If we do a push or a pop, that can move us here 1 step to the left or to the right. So that can at most make this potential go up or down by 1. And I multiply that by 4. So whichever way is the bad way, I get at most a cost of 4 from the change in potential plus the 1 actual cost. That sums up to 5. Okay? So far, so good? It's not necessarily very intuitive what happens. It's just following the argument for now. And so what a cheap push and pop does is it moves this black line one step left or right. And all that can do with the potential is, again, cause a change of 1. Then we have 2 expensive cases. We can have a push where we have to create a new array. And it turns out this costs us 2n plus 1. So I guess the 1 array access is to write the new element in at the end. And the 2n is for copying the elements over. I counted read and write separately. So you have n elements at the moment. You have to copy them to a new array. So you read the n elements. You write the n elements. That's 2n. And plus 1 is you have to store the new one at the end of the whole thing. What does that do to the credits? Well, for that, you have to look at where we are. When we are at the costly push, phi is 0 at this point, because we know that n is the same as the capacity. Otherwise, we wouldn't have the expensive push. So phi was 0 before, so we only have to look at what phi is afterwards. And so here we do our twice as big array, and it's filled up to half plus 1 element, right? That's where we are now. And you have to compute how far this is away from the 2 endpoints, the danger marks, full and quarter of full. And clearly this is the shorter in that case. The blue case will dominate, will give you the minimum. And that works out to 1/2 n plus 1 credits. Right? This is basically n, so it's half of it. And the plus minus 1, you have to write down the actual numbers and then see that that's the case. Insert a concrete n. If you sum up these 2 things, so the credits here, again, remember they get multiplied by 4, minus 4 credits, then 4. If you sum these up, the minus 4 times 1/2 exactly cancels the 2n. That's what you always want with these potential changes. You want them to cancel out the actual cost, the big part of the actual cost. And what remains is the 5, because we have 4 times this and the 1. So that's, I think is actually less by them, because it's minus 4. But it's at most 5. All right, still with me? Last one is the expensive pop. In that case, we had, before we must have had the situation that we're only quarter full. And now we copy it into a new array that's half as long. And again, the blue part will dominate because we're closer to this quarter mark again than to the right end. And so if you do the exact counting, there's a change here because you do a pop instead of a push at the end. So you're actually losing 1 more element here. But the same argument, the real cost is 2n. You have n elements in there. You have to copy them both, plus 1 more that you cancel out. And the credits were 0. Potential was 0 before, and it's roughly half n afterwards. You multiply that by minus 4, the 2n cancels, and what remains is again 5. So the magic at this point was, in all cases, the amortized cost was bounded by 5, a constant. And so why is this useful? if we have a sequence of m operations, and those could be any operations, we don't know, then let me maybe write this down. Let's say AI is the amortized cost of the ith operation. Then that's the actual cost, Ci, minus 4 times the change of potential. So we can say there's a potential after the ith operation, and then there's a potential before the ith operation, or after the I minus first. And we know that this is at most 5. That's what we lengthily argued here. So these are the AIs, amortized costs. And now if you sum up the amortized costs from all operations, 1 up to m, we know that this is at most 5 times m, because they're individually all bounded by 5. And we can rewrite the same sum in a different way by inserting the definition. If we split the sum up, then we have the cost of the sum of all the CIs, and minus 4, and then a sum that some of you may immediately see is a special type of sum, because this sum is called a telescoping sum. You're always taking a positive term from the next element and you subtract the previous, but you sum this up over the whole thing. So if you do this, they all cancel each other out. All terms occur with both signs in for 2 different indices I. So all that's really left of this sum is the first and last terms. So the very last one occurs only positively, and the first one occurs negatively. So you can rearrange this equation, the sum over the real cost, that's what we care about, the total actual costs. So I'm just rearranging this, bringing that to the other side. 5m is on the other side already, and I add the 4 times phi m minus 4 times phi 0. And for an upper bound, I can drop the second one because it's always non-negative. Okay? And that's what's written in this last line. The total costs are the total amortized cost plus the final credits, what I have at the end left. And total amortized cost is 5m, as we've argued. And the final credits, I don't know, but we know an upper bound for the credits. That's what we had up here. So it's at most that. And these two things together is some constant times m plus some constant times n. That's theta of m plus n. So what does that mean? If we do a sequence of m operations, the total cost will be at most some constant times m, the number of operations, plus the size of the array at the end. But really that's not more than the number of operations if you start with an empty stack. If you start with a stack that's already big and you do some operations, clearly it has to be taken into account that this was already big. That's why this occurs. And so C was the correct answer here. That's what we've shown with amortized costs. As a last thing, let me briefly argue why the others are not quite true. So the elements are not always stored in an array of exactly size 2n. N changes all the time. We don't exactly have that size all the time. This can't be true because we sometimes have to copy elements over. And the last is essentially correct, but any element is the catch. It's a stack. We can still just pop. Okay, that was maybe a mean one. Good. Apart from stacks, there's queues where you can insert at one end and take out of the other end. Otherwise, it's the same as the stack and the implementations are the same. and there's an abstraction of both of them. If you only have something that you can put elements in and you can get some element out, we call this a bag. These are just two terms that I want you to take with you. The implementations can be very similar to stacks. It's just different terminology. So a bag, you can throw things in and you get some element out with no guarantee whatsoever which element. And in a queue, you always get the element that was inserted the longest time ago, right? That's why for queue, people say it's first in, first out, and stack is last in, first out.